Okay. Since I got kind of further questions, I just want to answer this briefly about homework. So after today, after today's lecture, I will give you more problems on Sakai, and then I will make a grade scope assignment so that you should be able to turn in your homework at any point this weekend. And I'll set the due date on the homework for like the end of class Monday or something like that. Yeah, I think end of class Monday sounds reasonable. So all of the information about the homework is on Sakai, but then you do the homework on your own sheet and then turn it into the grade scope assignment, which will exist in 2 hours or so. Okay, so last time, we focused on some more compound propositions. So our current list that we have, if I'm not wrong, if we start with P and Q as propositions, we have propositions not P, we have propositions P and Q, we have propositions P or Q, and we have proposition P implies Q. These ones, I think, mostly people are fine on. P implies Q is a little more challenging. We started discussing this last time, and we'll go further today. So as a kind of warm-up to remind us about what we're dealing with P implies Q, I want y'all to answer whether the following statements are true or false, okay? So here's a statement one. If pigs can fly, then unicorns exist. Can someone tell me what the two kind of atomic basic statements are here, and then the truth value of this whole proposition?
The atomic statements are if pigs can fly,
Yep.
and unicorns exist. And although each individual atomic statement is false, the overall proposition is true.
Exactly. Right? The P implies Q is only false when P is true and Q is false. But that's not the case here. They're both false. So this proposition is true. If pigs can fly, then unicorns exist. Sure, that's a true statement. Similarly, if pigs can fly, then horses exist. What about this one? Is this true or false? This one's true for very similar reasons. Here, we have the same proposition P as the hypothesis, and pigs cannot fly. So this is once again false. And the moment that we have the hypothesis being false, the implication P implies Q will always be true. We don't even need to think about whether this proposition is true or false. If the hypothesis is false, then the implication statement is true. If pigs can fly, then horses exist. That's true. Lastly, let's do this one. If horses exist, then pigs can fly. Is this statement true or false? Yeah, exactly. This one is false. Thank you all for responding. Massive response. Very good. So here, the first proposition P is horses exist, and the second proposition Q is pigs can fly. And here, horses do exist, so the hypothesis is true, but the conclusion is false because pigs cannot fly. And this is the only case in which an implication, P implies Q, is false. The hypothesis is true, but the conclusion is false. And indeed, this kind of all makes sense with our language. These two propositions sound fanciful, but since the hypothesis can't be satisfied, you can't tell me that I'm lying when I say this statement. But here, if I say, if horses exist, then pigs can fly, you can say this is false because horses do exist and pigs do not fly. So you're wrong, is what you'd say to me. Okay, so this is just kind of warming up with our um, implication stuff. Any questions on this? No, it seems everyone's pretty comfortable with implications. Okay, then another question I have, and this is a little different, this is going back to our questions about P or Q. Was anyone able to find, was anyone able to write exclusive or as a proposition involving P and Q and ands, ors, and nots? So let me just kind of recall for you what the truth table of exclusive or is. So we have P, Q, true, true, false, false, true, false, true, false. Okay, so P exclusive or Q. Can someone tell me what the truth table ought to be for the exclusive or of P and Q?
False, true, true, false.
Exactly. False, true, true, false. Because this statement is P or Q, but not both. Yes, perfect. False, true, true, false. And exactly. Thank you, Val, for the answer. So a, and there are many, but a proposition using only P's, Q's, ands, ors, and negations, which reproduces this same truth table, is exactly P or Q and not, maybe I'll do a lot of parentheses here, not P and Q. And it's not too difficult to check that this will give the same truth value if you write out what P or Q looks like and you write out what P and Q looks like and you do the negation. So if you don't believe me that this proposition yields the same truth values as the exclusive or, then you should check this. It's not so difficult to check. But the point that I want to make is that one can guess that this is the right form using our language, because the exclusive or, when I write it out very carefully, is P or Q, and then I usually say but not both, but not P and Q. Or you could also say it P or Q and not P and Q. So you see that if you just try to describe this proposition, what does it mean to be exclusive or, you're led to a sentence which suggests the logical operators that you should use to get this compound proposition. Does anyone have questions about this little exercise that I gave y'all last time? No? No questions about this? Okay, that's cool. No questions, that's fine. What do I want to do? I want to talk a little bit more about implications and some other ways to kind of think about statements that come from implications. So more on implications. First, I want to bring up some other statements or other ways to write P implies Q. So here are some ways to write P implies Q. If P, then Q. This is probably how I first defined it, so this isn't surprising at all. Here's another one. P is sufficient for Q. The next one would be P implies Q. And then here's one that kind of tricks people up a little bit, trips people up a little bit, is Q is necessary for P. Q is necessary for P is another way of saying P implies Q, or Q is sufficient for P, or if P then Q. And there's a longer list in the textbook if you've read ahead, but I think these cover the most common ones. These three being the most common, and this one covers one that is true, but perhaps looks a little strange. Are we more or less comfortable with the first three? Okay. Would anyone like for me to explain a little bit more about why Q is necessary for P means the same thing as P implies Q or P is sufficient for Q? Okay, yeah. So Q is necessary for P. Let's set up the truth table. So we've got P, we've got Q, true, true, false, false, and true, false, true, false. Okay. And the point that I want to make about Q being necessary for P is the following. Usually when we think about P implies Q, we start with the truth values of the hypothesis, and then we look at the truth values of Q. But for Q is necessary for P, we should first look at the truth values of Q and then compare them to P. So maybe a wordier version of Q is necessary for P is the following. So wordier version of, oh, sorry, you can't see this so well. Q is necessary for P is how do I want to say this? A condition that must be satisfied in order for P to be true is that Q must be true. Though that may not be enough. Right, so I'm kind of replacing Q is necessary for P with a wordier version, but do you agree that the content of Q is necessary for P is that kind of a precursor to P being true is Q being true? Like a condition that must be satisfied in order for P to be true is that Q must be true. The first thing that you should check if you want to think about whether or not P is true is, well, first look at Q and see if Q is true. And then, and only then, should you then see if P is further true. Is it understandable how this longer, wordier sentence is trying to capture the same information as Q is necessary for P? Okay, so now what we should do is we should go down the lines and check whether it is truly the case that Q could be a necessary precursor to P being true. And here, Q is true and P is true. It could indeed be the case that Q is a necessary precursor to P. So Q is necessary for P. Here it'll be true, because it does indeed seem like Q is a necessary precursor for P. Here it's false, because Q is false, but P is true. So in this case, it is not the case that Q is a necessary precursor to have P. Right? Here you, if you think about it as like some of those like, I don't know, I'm thinking in terms of like nuclear bombs or something like that. Like, you can only press this button if so many other buttons turn green or something like that. Like, there are a lot of locks on P being true, and you can only have this unlocked if everything else is unlocked. But here, the precursor is locked, but the final button is unlocked. So this is not a necessary precursor. So in this case, the statement is false. Next, we say Q is necessary for P, but here is it may not be enough. Here, Q is true, but P is still false. Well, that's fine. It's still the case that Q looks to be a necessary precursor to P. It's just maybe you need more for P to be satisfied. So here it still looks like Q is a necessary precursor to P being true. And then lastly, if Q is false, then P is false. I think of this in the same way that, yeah, P can't possibly be true because already the necessary precursor Q is false. So this collection of truth values is consistent with Q being necessary for P. So if I were to summarize all that I just said, it was Q being necessary for P kind of flips the way that you think about it on its head, where first you look at the truth values for Q and you view it as is Q being true a necessary precursor to P being true? And the truth table that you get out of this is exactly the same as the truth table for P implies Q. Can I explain again, why is it true when P is false and Q is true? Right, so think about the following. Let's think of P as a button that we can only sometimes push, but this button is only unlocked if two other buttons are unlocked, say a button called R and a button called Q. So this is like a potential setup where you can, like, first you press this button, then you press this button. Oh, you can't see. First you press this button, then you press this button. And if you press these two buttons, and pressing a button here is the same as being true, then you can unlock P, and then P can possibly be true. So the point is, this stage, Q being true and P being false, could correspond to you having pushed button Q, but not having pushed button R, so you couldn't possibly have pushed button P. So it's still the case that Q is a necessary precursor for P, but maybe there's another necessary precursor for P which isn't satisfied. Right? It's possible to have multiple necessary precursors for something to be true. For instance, if I want to write a statement, I could say a necessary, so two necessary conditions for getting an A in my class, 381, are 1, registering for class, and 2, taking tests. So it's quite possible that you could register for this class. So this is like Q, and this is R, and this is P. So it's quite possible that you registered for the class, but you didn't get an A in the class because you weren't taking any tests. It's still true that Q is a necessary condition for P. It's just not sufficient. Okay, yeah, I hope this explanation wasn't too convoluted and kind of too much, but here's why it's still fine that Q is a necessary condition for P. It's just not enough to guarantee P necessarily. Any other questions on this? Okay. I hope that was clear and not more confusing. Okay, so let's introduce some related propositions. So let's say that we are considering the proposition P implies Q. Then there are several related propositions that we want to call the following names. There's the converse, which is Q implies P. There's the contrapositive, which is not Q implies not P. And then there's the inverse, which is not P implies not Q. Okay, so let me make the following exercise for y'all. Let's see, let's get some propositions. What's a good proposition P? Cats are not animals, great. And as Q, I'll take lizards have feathers. Tony Stark as Iron Man will be next. Okay, lizards have feathers. Okay, so what I would like to do is P implies Q is the proposition if cats are not animals, then lizards have feathers. Okay, so this is this P implies Q statement. Could someone either tell me with their voices or write out in chat what the converse statement is, the contrapositive statement is, and the inverse statement is? So the converse is if lizards have feathers, then cats are not animals. Very good. How about the contrapositive? If lizards don't have feathers, then cats are animals. Good. And then the inverse. If cats are animals, then lizards do not have feathers. Yeah, exactly. So these are a bunch of different constructions that are related to a proposition P implies Q, but they're related in different ways. So what I would now like for y'all to do is to write out the truth table. So P and Q. And then this is going to be another truth table exercise that I would like for y'all to do, and I'll do it slowly after you. Oh, one important note. For your homework, I would ask that you always set up your truth tables in this fashion. Have your first proposition be a whole bunch of trues and then a whole bunch of falses. Have your next one being the smaller blocks of true and false. And as we get on to when we have 3 propositions, I would ask that you kind of always do the same shape that I write them in, just so that our grader doesn't have as much of a headache. Okay, so what I would like for us to do is fill in a truth table with these different propositions. So P implies Q, we already know. True, false, true, true. But then I'd also like for you to fill in the truth tables for the converse. Q implies P. For the contrapositive, not Q implies not P. And for the inverse, not P implies not Q. So I'll give you a couple minutes to complete this. I'm sure this isn't too challenging, but I just want y'all to be doing a little bit. Although you've already translated the fun sentence into a bunch of different things. Okay, so I'm going to start slowly following y'all, but not saying anything so that you can still work. Mm. Did y'all finish your truth tables? Great, y'all are very fast. I'm very happy. So what do we note about the relationship between these different propositions? In particular, what's the relationship between the implication P implies Q and the contrapositive not Q implies not P?
Can you repeat the question?
Yeah. What is the relationship between this line of the truth table and what is the line of this and this line of the truth table? Yes, they have the same truth value. So whenever P implies Q is true, not P implies not Q is also true. So these two expressions have the exact same truth value everywhere. And it's the same thing with these two. The converse and the inverse have the same truth values everywhere because they're true in the same places and they're false in the same places. But in particular, we should note that these lines of the truth table have different truth values from P implies Q. So in other words, the converse is not equivalent to the original implication. the inverse is not equivalent to the original implication, but the contrapositive is equivalent. So what this means is that at any point in time, if you have a proposition that you're trying to understand, for instance, our fun proposition about cats and lizards, you can always replace it by the contrapositive and have a proposition which is true in exactly the same ways and false in exactly the same ways. So these will be equivalent. We'll talk more about equivalences soon. That's the content of chapter 3. So we'll be there shortly. Any questions about this? We're doing okay? Since there's no response, I will continue. Okay, so now let's go to biconditionals. So a biconditional is the following proposition. Definition. Let P and Q be propositions. The biconditional, and it has the following symbol, P and then an arrow heading both directions, Q, is the proposition P if and only if Q. And it takes this, and it takes the value true whenever P and Q have the same truth value. And false otherwise. Okay, so the truth table of this, I just wrote it in words, but let me also do it in symbols. So P if and only if Q has the following values. It's true here because P and Q have the exact same truth values. It's false here. It's false here because they don't have the same truth value, and it's true here. Can someone recognize P if and only if Q in terms of a, yes, Alex, you have answered my question as I was asking it. Exclusive OR has the same truth value as the negation of P if and only if Q. So what I want to write is the negation of P if and only if Q is exactly false, true, true, false. And this is exactly the truth table of exclusive OR. So in other words, P if and only if Q is the negation of P exclusive OR Q. Very good. Okay, so one way that I think of P if and only if Q is as a check or a test, whether or not P and Q have the same truth values. And it gives me a false whenever the truth values of P and Q differ. Okay, here are some other ways to think about P if and only if Q. What I want to write now are some more parts of the truth table. P implies Q has truth values true, false, true, true, and Q implies P has truth values true, true, false, true. Is this correct? Yes, this is correct. Can someone find a way to combine these two truth tables or these two lines of the truth table in order to get P if and only if Q? Yeah, exactly. Thanks, Catherine. So notice that if we do the and, or the conjunction of these two propositions, the conjunction, so I'll just write it like this since I have no space. The conjunction checks whether they're both true. They're both true here, so it's true. They're not both true here, so it's false. They're not both true here, so it's false. And they're both true here, so it's true. So in other words, the proposition P if and only if Q is equivalent to P implies Q and Q implies P. So these are several ways of understanding what the logical content of P if and only if Q means. Any questions about this? No? Okay. Let's say some other ways to write this. Also written as P is necessary and sufficient for Q. Notice that this construction is using kind of two of our previous constructions, because P is sufficient for Q is one of the implications, and P is necessary for Q is the other implication. So remember, P is necessary for Q. Is what implication? And Luke, it is correct that that Q if and only if P is equivalent to P if and only if Q. So P being necessary for Q is the statement Q implies P. Remember that the necessary thing kind of switches. So P implies Q is equivalent to Q is necessary for P. If I switch this, P is necessary for Q, that's the same as Q implies P. And then P is sufficient for Q is another way to write P implies Q. So P is necessary and sufficient for Q gives you both of the sides of the implication. Okay. Another way to write P if and only if Q, and one that I'll be using as a shorthand often, is, and this is not recommended for kind of formal proofwriting, but if I'm just trying to write in shorthand, P if Q with two ifs. This is the kind of non-rigorous contraction of if and only if, the if with two f's. So this is the same thing as P if and only if Q. So here are different ways that we can talk about this proposition, P if and only if Q. Okay. Any questions on these collections of compound propositions that we've built up? Okay, at this point, I just want to give a brief summary of what we have done in this chapter, or this section, which is 1.1, which is, you can think of it in two ways. The way that I think about it is we have introduced a bunch of ways of building new propositions out of more basic propositions. And you can essentially think that we are taking symbols and assigning kind of rules for what the truth value of this symbol is in terms of the truth values of P and Q. That's one kind of very abstract way to look at it. The second thing is that we have tried to link these symbols to statements in our language such that it makes sense to kind of translate back and forth from a symbol like this to a statement in language, like horses fly if and only if lizards have feathers, and then try to understand whether or not this is a true or false statement based on whether the constituent pieces are true or false. So there's an abstract aspect, which is just the definition of these lines of the truth table. And then there's the translation aspect where we say, is there a good way to think about this proposition in terms of our language and in terms of the smaller propositions? Is that okay? No one's complaining, so I will continue. Okay. So we're going to entirely skip section 1.2. Is skipped. And we're going to go right into 1.3, which is propositional equivalence. And you will note that propositional equivalence is something that we've already kind of discussed and we've been kind of dancing around the edges of. So the basic idea is we want to understand when different propositions yield the same truth values. So an example that we've already done and already worked with is P implies Q, and not Q implies not P. The point that I want to make is that these are different propositions because they're different propositions because they are, like, if you wrote these out in words, they'd actually be different statements, right? One is working with the negation of Q and one is working with Q. The order is switched, yada, yada, yada. So these are different propositions because they're different statements. However, they deserve to be called equivalent propositions. And why is that?
They yield the same truth table.
Exactly. They yield the same truth table. In other words, if you're trying to assess whether this statement is true or false in any given situation, you can either work with this statement or with this statement. They're interchangeable for the purposes of understanding when something is true or false. Okay. So what we're going to define here is a kind of rigorous and internal way of describing equivalence of propositions. And before we do this, we need a kind of further definition. A compound proposition which is always true is called a tautology. A proposition which is always false is a contradiction. So oftentimes in symbols, we will use the symbols kind of T or F. So T would be a line in the truth table, which is always true. So for instance, I can make a truth table out of P. P can either be true or false. Then I can also make a truth table entry for a tautology, which will just give me true and true. And now I can work in the exact same way with this proposition tautology, in the same way that I can work with any other proposition. For instance, I can ask, what is the truth value of P and a tautology, or P or a tautology, or something like that. And the same thing for false. So false is the proposition, or a proposition, which is always false. Question. Can we write a tautology using like P's and Q's and ands, ors, and negations? How do I spell that T word, tautology? Tautology. Yeah, my handwriting is terrible, so please continue asking these questions.
I'm gonna say yes, but I'm not sure how you would do it.
Yeah, so let's first try working with a tautology. So let's think about P, which looks like true and false. And now let's remember the or the disjunction of two propositions. Yes, exactly. And think about not P, right? Not P is going to take the exact opposite truth values, so false and true. And now let's remember that there is a compound proposition which is true when at least one of the two constituent pieces is true, right? If I do P or not P, let's consider, is it going to be true here?
Yeah.
Yep. And is it going to be true here? Yes, exactly. So one way to build a tautology logically is to take any proposition and then take the disjunction with its negation. And this kind of makes sense because recall that all propositions have to be either true or false. So I can take any proposition like lizards have feathers, and I can immediately make a proposition which is always true by making the proposition lizards have feathers or lizards do not have feathers. Right? This is always going to be true because either lizards do have feathers, either this is true, in which case this is false, but still, since one of them is true, the whole statement is true, or lizards don't have feathers, but then the statement lizards do not have feathers would be true, so one of them would be true. So this construction, taking a proposition or its negation, will always be true. This is a way that you can build tautology out of any proposition, P or not P. Do we agree? Great. So that's how we build a tautology, or that's one way to build a tautology out of any proposition. Can we build a contradiction? How do we build a contradiction out of a proposition? Yeah, exactly. Proposition and its negation. So P, not P, has truth value true, false, and then this has false, true. But instead of taking or, we could take and, P and not Q, or P and not P. Now remember that and requires both of the entries to be true in order to be true, otherwise it's false. So false, false. Or in words, if I take an arbitrary proposition like Tony Stark is Iron Man, then P and, so P is Tony Stark is Iron Man. And then the proposition that I build, P and not P, is Tony Stark is Iron Man and Tony Stark is not Iron Man. You put in any truth value for this statement, and the second statement will be false. Well, if you put in true for the first statement, the second statement will be false, so their conjunction is false. If you put in a false statement for the first statement, then the second statement will be true, and the conjunction of a false statement and a true statement is false. This statement is also always false. It can never be the case that Tony Stark is Iron Man and also not Iron Man. Any questions on this? Oh my gosh, it is already time to go. Okay, great. Well, we got to tautologies and contradictions, and we will be using these very often for the rest of class. They seem kind of basic and simple, and they are, but they are surprisingly valuable and useful tools. So thanks for listening to me, and thanks for participating, and have a lovely weekend.
Thank you.
Yeah, absolutely. So long.
Thank you.